Related to yesterday's session. I will post that very soon, maybe after today's session. So anybody having any discussions or any doubt on the previous session? So here is the notes, whatever we had written. So remember that I'm not doing exhaustive derivations for the lack of time, and we want to accelerate the process. So some of the derivations I'm just giving you with some assumptions and trying to cut short some of those derivations, conceptually explaining some of the things. But for more detailed derivation, you have the textbook, you can go through that. But conceptually, we are trying to, understand some of the important concepts that will be required for any project. So yesterday, just a quick recap. We discussed the inverter characteristics, the transfer characteristics of the inverter, the concept of noise margin, right? And also the operation region of transistors in the different region of the transfer characteristics. Then we also looked into the sizing effect on the transfer characteristics. What happens if you increase PMOS size, NMOS size, how the transfer characteristics will shift, and also the concept of the trip point, how the trip point depends upon the sizing. We discussed that. Why do we try to keep the trip point midway? That also we discussed. We discussed the effects of this transfer characteristics and the trip point on rise time, fall time, duty cycle, etc. Right? We discussed that also. The effect of trip point on rise in the duty cycle and rise time, fall time. Or basically the sizing effect on rise time, fall time, like PMOS sizing, what happens, NMOS sizing, what happens, what is the effect on rise time, fall time. We also discussed the sizing for an appropriate trip point for NAND gate and NOR gate, like what is the sizing ratio required for a midway trip point for NAND gate, NOR gate. And finally, we were discussing the use of this inverter as an amplifier. Right? How do you make it work as an amplifier? So we discussed the biasing scheme. Why do you need an R? And also, some sizing issues. How do you increase the gain, etc. Bandwidth issues. If you are using a coupling cap for applying the input to this inverter, how do you size the devices? What is the R going to? How is the R going to affect the characteristics? Those things we discussed. So any question before we go to the next step? Any question before we go to the next step? Nobody has any question? Okay. So going forward, so unless you ask questions, things will not be clear. So in case any part is not clear, you are, if you're not asking question, you will be wasting your time, because you will have to either you will not understand those things, or if their doubts are there, you are not asking. Probably those doubts will remain as it is. So today we'll touch upon some more related topics. One of them is process variation. Process variation. What is process variation? So we discussed, am I audible clearly to all of you? Like the volume, etc. is okay, or is it low? Volume is okay.
Okay.
So last time we discussed the effect of the inverter sizing on the transfer characteristics. Like, the transfer characteristics can shift either this way or this way, depending upon the PMOS and NMOS strength, right? So now when a chip is fabricated, so in the fabrication process, I hope all of you are aware how the basic fabrication step works. So you can have a silicon wafer, right? So how the production happens. So I think EC people might have gone through this. So EC people might have gone through the fabrication process of integrated circuits. What about EE people? The fabrication process, the wafer and the masks for the chip fabrication. Have you gone through any such discussion in your classes?
No.
Okay, so very quickly I will discuss. Probably it would be good to use some slides there, but right now I'm just going to draw and explain. So first thing is that for the fabrication process, there is a silicon ingot. So there is a very highly purified silicon, something like a log, and from there we basically create wafers. So these wafers can be say 1 feet, 12-inch wafer, and from there, we are slicing this silicon ingot, highly pure silicon ingot, into wafers. Wafer thickness may be just few micrometers, and the diameter may be 12-inch or maybe even bigger. Some are smaller also, but I'm just taking one nominal value of 12-inch diameter. Now this 12-inch diameter silicon wafer, it is like a circular disc, very thin circular disc of silicon. And on this thin circular disc, we fabricate the ICs. The way it is fabricated is we print the ICs. We print the ICs in this circular disc. We divide this circular disc into multiple segments of, say, given dimension, and the design that you have implemented will be copied into or printed into each of these sections, and then it will be cut out. So this is called dicing. So dicing. This is silicon ingot. This is wafer. And from there, this is a die. So after dicing, you cut and get the individual chips, which are the silicon chips on which your circuit is fabricated. So when you do a single design, you may get multiple copies. So in the fabrication process, you may have, say, 20 copies of the same chip. So 20 such segments may carry the same design. That can be specified by the fabrication setup. It is also possible that the entire wafer is having the same chip. So multiple chips are coming out from the same wafer. All the chips are having the same design. Or it is also possible that different dies, different segments have different designs. So now how this fabrication process works. So the fabrication process, if I look at the fabrication of transistors, right? So the very first step is that suppose you have you at least know the doping concept, right? All of you are aware of the doping concept, N-type doping, P-type doping, right? All of you are aware, doping of semiconductors, doping of silicon.
Yes.
E people specifically, because you have not covered the device part, but all of you have been given derivation of the MOSFET current, PN junction diode, diffusion current, drift current, how the diffusion region, how the depletion region of the diode depends upon doping, how the currents depends upon doping. All those things you have been derived, right? So you have been given all those explanations in your introduction to electronics or analog digital electronics, right? Yes, you have to speak quickly. Means you have to respond yes or no fast.
Yes, sir.
I'm not hearing anything. Miss, what is going on? Are you able to hear me? I need the response.
Yes, sir.
Yes, can anybody explain? What do you like? Anybody's means I need how many people are aware of the diode characteristics, like the diode physics derivation, current density derivation, drift diffusion current derivation based on the doping concentration, etc. How many of you are aware? Diode equation, current equation that is derived. It depends upon device structure, the device dimension, doping concentration. So how many of you are aware of the diode current equation and its derivation? How many of you have been taught? Can you raise your hand? Nobody's raising hands. So that means none of you have been taught. Basic electronics, I think for you people, basic electronics or introduction to electronics was scrapped, right? There was no introduction to electronics.
No, sir.
Yes, sir. It's not there.
And then in the analog electronic circuits or digital electronic circuits, this topic was not covered, like the diode derivation, diode semiconductor equation, the drift diffusion currents, those things were not covered.
No, sir.
Very strange. And without that, how are we supposed to understand? So maybe these things will be covered later, but these are basic things. And earlier in the introduction to electronics course, this were covered, and somehow currently it is missing. So in analog circuits also it was supposed to be covered. Without that, you don't understand device characteristics. Then I will have to give you some reading assignments from some books, and you will have to go through that, because I will try to cover briefly in the class, but these are basic things. The device, the device structure, device fabrication, and also the basic current derivation. So the current derivation of the MOSFET, like the quadratic region current and the triode region current, those derivations have been done for you. Like for the BJT also, the current derivation, the exponential current for the BJT, that has been given to you, like taught to you. Yes,
Yes, sir.
anybody?
Yes, sir. We have done for the BGT and the MOS. We have done.
So BJT, when you have the current derivation, so you must have studied the diode, right? Without diode, how do you go to the BJT current equation? Because the BJT current equation depends on the diode. So the diffusion current and the exponential dependency all comes from the diode equation. So if you are saying that BJT current derivation has been covered, so how come diode derivation has not been covered?
So the diode we had just stated, and it was not derived on a great detail, and neither was the BJT. Like, it was just mentioned for the diode, and also for the BJT, it was mentioned for MOS. We did the derivation.
Then a lot of things are missing, and covering everything. I will have to give you some. You are saying anything, Nafisa? Anyway, so your hands are raised. If you don't have to say anything, put your hands down. So the question is that, if you have to cover everything, it will take time, all the derivations of the current equations. So first I will give you a reading assignment. And once we are done with that reading assignment, then only we will go and have a discussion in the class. Otherwise, if those basic things, if I have to cover each and every detail, it will take good amount of time. So once you are gone through that chapter, read those chapters, then it will be easier to discuss in the class. I will be able to cover it quicker. So first I will give you that reading assignment. But anyway, so now I have to keep in mind that those things have not been covered in class as far as the device concepts are concerned. So despite that, we can proceed and we try to understand how the fabrication is done and what are the issues related to process variation. So now for fabricating the circuits or the transistors devices on this wafer, we need doping, right? For a PMOS, NMOS transistors, we need the substrate. For PMOS transistor, what kind of substrate do we need? What kind of doping do we need in the substrate? PMOS substrate, what kind of doping do we need?
So we need elements which have lower valence electrons than 4. That is, which can produce holes like magnesium and boron, aluminum.
I said for
P-type.
NMOS, what kind of substrate do you need? N-type dope or P-type dope?
For NMOS, we need a P-type substrate.
Yes, so for an NMOS structure, all of you have seen, right? So NMOS structure is something like this. I hope the recording is going on, right? So recording, let me see. Yes, recording, I guess it is going on. So for the NMOS structure, we have a P-type substrate and we have N plus source and drain region, right? This is N plus source and drain region. and there is a gate oxide, and there is a gate contact. This is your gate. This you can assume as source terminal. This is your drain terminal. And then there is a substrate, which is P-type doped. We also have a body contact. How do we make a body contact? In the MOSFET, you might have seen symbol like this, right? So in your lab experiment, also the devices that you have used, it may have 4 terminals, including the body. So gate, drain, source, body. So how do we contact the body?
So from the substrate, the P-type substrate as a body contact.
So you need a P plus contact. So P plus, and then you take a body contact. So assume that I'm looking into the cross section of this, wafer. So I am looking into cross section of this wafer. That means along the edge, right? So I'm looking at the thin cross section of this wafer. That means after you cut the die, you have this kind of structure, right? Once you slice the die, the MOSFET is getting fabricated somewhere here on the top of this die. You are looking into this structure, right? If I zoom it further, this die after cutting, it is something like this. And you are looking at a MOSFET being fabricated somewhere here. You are having some N-type doping, P-type doping, and a MOSFET structure being formed over here. So I'm looking at the cross section. So all of you are aware of this cross section view of the MOSFET. This cross section view that I have drawn. Are you aware of this cross section view of MOSFET?
Yes, sir.
Yes, sir.
And what will be the top view? So this is something like I am looking at the cross section view from here. If I look at it from the top, how will it look like? This will be the gate region. And on both sides, you will have source and drain region, right? This is your source, drain, this is your gate. And there will be some contacts. Here also there will be some contact. Ultimately, these wires that I have drawn in physical structure, this will be like metal contact, right? This will be metal contacts. So the top view is something like these are N plus contact region, source, drain, diffusion region, and it is sitting on the P-type substrate. So the below this P-type substrate is there. These two are N plus region, and there is a gate. Below that gate, of course, there is a oxide. So if I want to have some more clarity, I can also draw the 3D view of the MOSFET. So 3D, how will it look like? So the 3D view will be something like this. And the channel is somewhere here, right? So this is gate, oxide is there. So this dark region, you can say this is oxide, which is lying just below the gate material. What is a gate built of generally? So this thick, the dark.
Insulated layer of oxide. Metal oxide.
Sorry,
There is an insulating layer of oxide.
the oxide is this one. Why is it getting deleted automatically? So this dark thick line that I have drawn, that is oxide. What oxide? SiO2. This is dark one. And this gate is polysilicon. So the gate material is polysilicon. Below the gate, there is SiO2, thin layer of SiO2. Polysilicon is something like a metal which can have higher conductivity. And polysilicon is generally doped. So you can have a doped polysilicon. So polysilicon is different from crystalline silicon. So the silicon MOSFET, the substrate is crystalline silicon. This is also silicon, but it is crystalline. This silicon crystal, it is basically a lattice structure, a proper lattice structure of the silicon. But polysilicon is, as the name suggests, it is a polymerized kind of silicon. It is not having the standard silicon tetrahedral structure. So the polysilicon structure, it can be doped to have higher conductivity. It behaves like a metal. So if you have a highly doped polysilicon, you can assume that it is acting like a metal contact. So generally, what is the MOSFET structure stand for? MOS. What is MOS? What does MOS stand for?
Metal oxide.
Metal, oxide, and semiconductor. So here the metal role is being played by the polysilicon, highly doped polysilicon, which can have higher conductivity. Oxide is SiO2, thin layer of SiO2. And the semiconductor is the crystalline silicon substrate. This is the MOSFET structure. So of course, the substrate is going to be thick, right? Because the substrate thickness depends upon this thickness. And ultimately, that depends upon the wafer thickness in the direction perpendicular to the plane. So silicon is supposed to be sufficiently thick. This can be several micrometers, several tens of micrometers to 100 micrometers. So that substrate is thick. And on the top of the substrate, you are creating this MOSFET. And this is the cross-section view of the MOSFET, and this is the top view of the MOSFET. So cross-section means you are seeing from the front, right? So looking at it from the front, this is the cross-section view. And looking from the top side, you are getting the top view. So this is your top view, cross-section view. Are you able to, again, there is going to be a body contact that I have not drawn, but you can also, create a P plus region, and that will give you another, a body contact region. This is, the body contact. So this can be your source, this can be your drain, this can be your gate, and this is your body contact. So are you able to relate from this 3D structure to, are you able to relate this to cross-section view and the top view with this 3D structure easily, or any problem?
Yes, sir. Yes, understand.
Anybody having any problem in relating this top view and the cross-section view with this 3D structure of the MOSFET? Anybody having any problem? Don't hesitate. If you have any problem, feel free to interrupt. So where is the channel? The channel, you're going to get the channel. Where is the pen? The channel will lie here below the gate in the silicon. So if it is in saturation, it will be slanted, it will be pinched off channel. So the channel is here. This orange region is a channel. And why do we need this? This is the P substrate. Why do we need a P plus over here? For body contact, why are we putting P plus? Anybody knows why are we putting this P plus? P plus means what? As compared to the P doping, P plus is much more highly doped. Right? So why we use P plus for contacting the substrate or the body of the PMOS? Anybody knows? So there is something called contact resistance, right? So ultimately, if you have to make connections with these MOSFETs, you will require metal connections. And if metal directly contacts the silicon, if you are trying to connect a wire or a metal connection with the silicon transistor, it will form a junction, because metal, when directly connected with the lightly doped silicon, it will have a work function difference and it will create a junction barrier. It is something like connecting a very highly doped N-side semiconductor with a lightly doped P-type semiconductor. It will create an energy barrier. It is called Schottky diode. How many of you have been taught Schottky diode, Schottky junction?
Yes, sir.
Where did you study Schottky junction?
Studying the devices course, semiconductor devices.
So probably I will try to cover these things a little bit more detail. So for the time being, you just assume that the P plus contact is required to have reduced contact resistance. If you don't do this, if you directly contact the metal with the lightly doped P-type silicon, it will create higher contact resistance. So this P plus thing lowers contact resistance. And it prevents the formation of Schottky diode. So that part we will discuss. It requires energy band diagram for discussion. Those things, will require, an extended session. But for the time being, assume you should remember that directly contacting the silicon with metal will create Schottky junction. It will create higher contact resistance. We therefore apply a high dope region. We select a pocket where we heavily dope that silicon and then connect with the metal. So for P-type substrate, we have a P plus junction, and then we apply the metal, right? We are not applying a N plus junction because again, it will form a diode, right? The substrate is P. So P to P plus, and then go to metal. That will have reduced contact resistance. So for forming contact with the metal lines or metal interconnects, we put P plus junction. Likewise, the source drain anyway are N plus, because the source and drain regions are the, they are supplying the majority carriers, or basically the electrons which are going to be responsible for the transport of current. So the current in the NMOS is mainly due to the flow of these electrons from the source region to the drain region, right? So ultimately, the source region is going to supply electrons, and drain region is going to sink those electrons. And as a result, the electron current flow is from source to drain, and the electric current flow, which is opposite direction, it is from drain to source. So that part everybody knows. How many of you have been given the derivation of the MOSFET threshold voltage? How does the threshold voltage depend upon different device parameters? MOSFET threshold voltage derivation. So it depends upon, VT, if I say, is a function of what? What all parameters? Anybody remembers?
So one is the potential between the source and the body if they are not shorted, the VSB.
Suppose that is not a fabrication parameter that can be controlled later. Forget about source and body, assume that they are shorted. Tell me about the device parameters. What device parameter the MOSFET voltage, threshold voltage depends upon?
Phi is
What is phi here?
difference between intrinsic and Fermi level.
Sorry, difference between?
That intrinsic level and Fermi level. That
There's something called work function, phi ms. Phi ms means metal semiconductor work function. That is the Fermi level, the difference between metal and a semiconductor. So that is one parameter. What else? This phi ms depends upon the doping of polysilicon. This can be controlled by controlling the doping of polysilicon. Generally, we just use the term poly. For polysilicon, we can just generally refer to it as poly. So phi ms can be changed by changing the doping concentration of the polysilicon structure that you see here, this particular, this green region. What else does it depend upon?
Thickness of the oxide layer.
Thickness of the oxide layer. What else?
Doping of the P substrate. Doping concentration of the P-type substrate.
Doping of the p-type substrate. I'm stating it as Na. That means acceptor type doping. That is the doping of the p-type substrate. What else? Anything else that you can think of?
Surface charges on the oxide layer.
The trap charges, if you have defects, etc., you have some trap charges. It may depend upon that as well. But for the time being, let us ignore that because that is a more kind of random parameter, and that depends on the technology. So more deterministic parameters are these. So the surface charges that you are saying, it is more dependent upon technology. Different technologies may have slightly different, trap charge concentration. So for the time being, let us ignore that. So now these parameters. So conceptually, if I say, how does it, like if you at least talk about say TOX and Na, that means the oxide thickness and the doping concentration of substrate. How does the threshold voltage depend upon these? Conceptually, how do we understand? Without going too much into the derivation, conceptually, if I have to understand, how does the threshold voltage depend upon the doping concentration or the threshold voltage, the oxide thickness?
VTH comes down as we reduce the thickness of the oxide.
So why does that happen?
Like that increases the COX of the MOSFET.
Yes. So if you look at the MOSFET structure, if I am just drawing the cross section, you have the oxide. This is the TOX thickness of the oxide. This is the metal, contact. This is metal. And below that, you have the silicon P-type. And then on the other side, you have the source drain N plus regions. And you're trying to apply some gate voltage over here, VG. Assume that your source and body both at ground. So Vs is equal to 0. Body is also 0. Drain is at some slightly higher potential, Vd greater than 0, something. And then you are trying to increase the gate voltage. Starting from 0, you are going on increasing the gate voltage. This is oxide. So now, if I look at the overall structure, simply if I look at the amount of band bending. Now, band bending, the thing is that if you have not covered the band structure, you will not be able to understand band bending. So the other way to explain this will be that you have. I guess without band bending, if I have to explain this, so if you have the oxide thickness and the metal gate, I'm just thinking how to explain this without invoking anything related to energy band diagrams, because E people have not. So how many people, E people, are still there? Let's see. Can you just raise your hands? How many E people? Because I hope that some gap is there definitely, but we will bridge those gaps. E people. So we have 6 EE people as of now. 6, 7. 7 EE people. So that number has reduced. Earlier it was slightly higher. 7, 8. Okay. All the E people, please raise your hand quickly. E people. Okay. So we have around we have 8 E people as of now. So definitely that number has, this seems reduced, but we understand that the device course has given some advantage to EC people, but whatever is the gap, we will try to bridge. I will give you some reading assignment. If you go through those reading assignments, whatever is remaining, whatever additional discussion is required, I will cover that in the class. And I will also give you some of my own recordings where the device concepts have been covered in some more detail. I think the NPTEL lecture also that I have given you, initial couple of lectures are more on device. all of you, if you have gone through it, at least the basic device structure, etc., should be getting clear. I will have to check whether I had covered more basic things like the derivation of diode equations and the device structure, its effects, its dependence on all these device parameters. But I think those are covered there also. So in case you have gone, through, those initial lectures, you should have at least got an idea about the device structure, and it depends on the device parameters. But anyway, so here, if you're talking about the gate voltage, you're applying a higher and higher electric field. So when you're applying the gate voltage, you are creating an electric field from gate to the silicon. And if you have thinner and thinner oxide, you will have more and more electric field, or basically more and more potential drop in the silicon as compared to the oxide, right? Metal has no electric field drop ideally. So if I look at it, in the metal region, you will not have any electric field drop, any potential drop. So there is the gate potential is at some VG, which is higher than 0. You are going on increasing it. The substrate potential is close to ground because you have a N plus body contact. This is VB. You have set it to 0. So the entire substrate is close to 0 volt, and you are going on increasing the gate voltage. Therefore, in this vertical direction, there is an electric field from the positive potential gate voltage towards the zero potential substrate. And in metal, there is no potential drop, right? There is no static charge inside the metal. There is no potential drop across the metal. So this applied potential VG will appear across the oxide and the silicon. So this VG, we can sum it up as VOX plus V silicon. And this VOX will depend upon what? VOX will depend upon the thickness, because whatever electric field is there, that electric field times TOX will be the VOX. So this VOX is nothing else but the electric field inside the oxide times the TOX, times the thickness. Electric field times the distance is the potential drop across the oxide. And remaining potential is VSI, which is dropping within the silicon. So whatever potential drop appears within the silicon, that is responsible for creating the channel and starting a current flow. So we would like to maximize the potential drop across silicon and minimize the potential drop across the oxide. So definitely, if you have lower and lower oxide thickness, you are allowing a greater portion of the gate voltage to drop across the silicon, and as a result, you will be able to turn on the device with a lower voltage. Is that clear to all of you? This high level explanation is clear to all of you? Any problem?
Yes, sir.
So therefore, lower oxide thickness means lower VT, that means lower threshold voltage. Higher oxide thickness means higher threshold voltage. Simply because if you have a higher oxide thickness, a larger portion of the gate voltage that you have applied will be dropping across the oxide, and a smaller portion will be dropping across the silicon. So definitely, if you want to have more control of the gate on the channel, you need to have thinner oxide. That is the major idea. So the transistor, what does the transistor term suggest? What is the meaning of the term transistor?
Transfer of resistance from one side to another. Basically, transfers the resistance.
Transistor means you are controlling the resistance between two terminals using the third node. So there's a trans current flow. The current flow is between two terminals, source and drain, but that is being controlled by the third terminal, VG. So now in this case, by applying a higher and higher gate potential, you create an electric field, and that electric field ultimately if you have an electric field in the silicon region, what happens? You remember from your diode physics, what happens? If you have a p-type silicon and then you are creating electric field in this direction, what will happen?
So the minority charge carriers, that is the electrons, will be pulled towards the gate, and there will be a
Yes. So
end.
generally the p-type silicon will have holes all around. The uniform hole density will be there, which will be dependent upon approximately the donor concentration. So if you have donor concentration Na equal to around 10 to the power of 15 per centimeter cube, you will have that many holes in that piece of silicon, depending on the dimension and the doping concentration. Now, when you apply a positive potential, the holes are supposed to be pushed down. They will be pushed away, right? So all the holes will come down, and the minority, electrons, they will be accumulating near the channel. And as a result, the channel formation takes place. In simple way, this is the mechanism. That's why we need a positive electric field. That's why for NMOS, we need to apply a positive gate potential, which will conditionally create the channel by pulling the electrons close to the surface. And then there is a continuous channel formed between source and drain, and the current can flow between source and drain. If you remove that positive potential, then that channel is gone, and in between the source and drain, you have a p-type substrate, which is not going to allow the current to flow. Is that clear, all of you? Therefore, we need a larger portion of the gate voltage to drop across the silicon, and lesser oxide thickness will be helpful for that. Likewise, what can we say about the effect of the doping concentration? So if you have, say, a higher doping concentration, how will it affect the threshold voltage, and why? Yes, anybody? Yes, quickly. How will the doping concentration affect the threshold voltage?
The more the doping concentration, higher is the threshold voltage.
Sorry?
More is the doping concentration of the p-type substrate, higher is the threshold voltage.
Lower doping concentration has higher threshold voltage. Why? What is
No,
the
lower has
understanding?
lower doping concentration has lower threshold voltage, sir.
Okay, so what is the reason?
So it's like we have to bend the band more in order to make it in to transit from for inversion to happen. So we need higher potential. And if doping concentration is more, we need to we require more depletion charges, and that will cause a higher potential drop.
Okay, so in simple words, if you see, anybody else can explain in simple words?
That if you have a higher doping concentration in the p-type, since Na-Nd equal to Na squared, that's why that will create the that will lower the concentration of the minority charge, that is the electrons. So we will, to form a channel which is able to conduct, we'll need to apply a higher potential, because now the electron density is less in the p-type substrate.
Yeah, so because that is also another way, because if you have higher doping concentration, that means Na is high. That also means that the electron concentration in the bulk or in the substrate is lower, right? And if the electron concentration is lower, you need to, first of all, you need to apply higher gate voltage to push the higher number of electrons, sorry, higher number of holes, because if the Na is going higher and higher, you have to apply more and more positive charge on the gate to push more holes downward, right? Then only the holes will be depleting from that region, and you will have electrons accumulating. So larger number of holes, larger doping concentration will require higher gate potential, because gate potential in turn translates to positive charge. Higher is the positive charge, it will be able to repel more holes from the surface. So that means if your doping concentration is more, you need more positive charge on the gate to repel those more higher number of holes in the substrate to create the channel. And as a result, it is also going to increase the threshold voltage. So again, without going into the device physics, high level, argument, and just trying to say what is the effect of oxide thickness and doping concentration on the threshold voltage. So with the your oxide thickness, if you have a higher oxide thickness, it will increase the threshold voltage. If you have a higher doping concentration, it will increase the threshold voltage. So for the time being, we can understand these two parameters are going to have an impact on the threshold voltage. Likewise, there is also something called the work function. Work function difference is the Fermi energy difference between the metal and semiconductor. Again, that will require energy band diagrams to explain. I'm skipping that, but that also depends upon the doping of the poly. So polydoping will decide the phi ms work function difference between the metal and the semiconductor. That also adds to the threshold voltage. So doping of the substrate, doping of the polysilicon, oxide thickness, all these parameters will decide the threshold voltage of the MOSFET. So now, the reason behind describing all this is ultimately to understand the implication on the circuit that we are trying to build using this MOSFET, because a chip will have many transistors, large number of transistors, and we will have the fabrications of these transistors on that entire wafer that we just saw, that circular disk. Now, in the fabrication process, the way it will happen, the starting point, if I look at the steps, right? The step one, if I look at it, it will be like, okay, you dope. First, you start with the silicon. This is the piece of, the wafer. I'm just looking at the cross section. You first dope it with p-type. Right? You have p-type doping. So the entire the silicon is doped with p-type. Now you have a p-type wafer. The entire wafer has been doped p-type. Second step will be that now I can oxidize. I can create a very thin oxide layer on that entire silicon wafer. So I will do oxidation. And I will create a small thin layer of oxide, the dark insulator layer that you saw, that is created on that silicon. This is P, and this is oxide, POX, this thickness. Now, wherever I have to apply the source and drain, I will etch and open that area. So suppose I have to create source and drain here. So I will etch and open this area. So this is p-type silicon, and I have this, the oxide etched open. This is called etching. So the thin oxide layer has been opened in these pockets, and then I will dope those regions using, I will apply doping here, N-type. Now I will apply N-type doping. Now, because these are covered with oxide, so the doping will act only in the open region, right? So the doping will act only in the open region. Now it will create N plus. And also wherever you have to do P plus, you will have to open it again. So, in order to get the contact of the body, you have to go to the next step and again open a pocket for the P-type doping and apply P-type doping. So here, once you have this N plus, you have the source drain created, and you have the, gate region created. And then you can go for the contact deposition. So there are several other steps. You have to deposit the field oxide. So this is the N plus region created. Now you need to make the contact with the source drain gate. So for that, you can first deposit a field oxide on the top of this. That means a thicker oxide. Remember, this is your oxide which is obtained from oxidation. This is not deposited. the whole wafer is oxidized and you get a thin layer of oxide. But after that, the field oxide is deposited. So on the top of this layer that you have created, you deposit a field oxide. N plus, and this whole thing you cover with field oxide, SiO2, but field oxide. Field oxide is more amorphous in nature. It is less, the structure is not very well organized, and it is coarser oxide. Whereas the oxide that you grow here, that is in very fine tune with the silicon. So whatever silicon you are having underneath, you have grown this TOX, a very thin oxide, by oxidizing that entire layer, with a very well controlled process. How much time you are exposing it to the oxidation process, it depends upon that, and also the temperature, etc. So the temperature, time of exposure, etc. will determine how much TOX you are having, and that TOX will determine what is the oxide thickness, and that in effect will determine what is the threshold voltage. So this has to be very precisely controlled for how much time you are oxidizing it, at what temperature you are oxidizing it, and also other parameters like doping, etc. will also influence the rate of oxidation. So all that will decide the oxide thickness and in turn the threshold voltage. And now once you have the field oxide, you have covered this entire thing with field oxide. That means it is now you can, if you have to take the contact, how will you take the contact? Again, you have to etch open some of the region. So suppose now you want to have a source, drain, and gate contact open. So now you will etch, you will create basically, so how these things are, how this, okay. Wait a minute. So something is happening. Only I can, so this one. So in order to etch open now and create the contact, I will again create, I will etch these areas and deposit metal. So I can, etch these areas and deposit metals so that, I have the contact to this source drain region. So this red color thing that I'm showing, it is a metal layer. So you can have the metal contact going into the source and drain region through this field oxide. And then actually these are acting like wires, but ultimately these are like metal layers. And this is like the via. We call this term as via. Via means it is connecting, say this is the metal one layer. This is the metal one layer M1, and M1 is connecting with the source drain region and the gate region using these vias. Vias run vertically in the field oxide. So overall, this is the process roughly for the fabrication of MOSFET. Likewise, how do you form NMOS? This is what the NMOS. How do you form the P MOSFET?
Sir, we'll take an N substrate and then form wells, P plus wells for the drain and the source, and then we'll have an N plus well for the body terminal.
Okay, so again going very quickly back to the discussion. Where is the mouse? So somehow the mouse gets missing somewhere. Where is the cursor? Wait a minute. So this is the one. So going down a little bit. Why is it not allowing to move? Wait a minute. So I'm trying to drag it down, but it is not working. Something is wrong. Something gets stuck and I'm not able to move. Okay. Now another thing is how these things are being done. So I told you, even the etching process, right? So if I elaborate this third step, etching, right? I call this process etching, where you remove the oxide TOX from some regions to create the source and drain. So what is the process involved in that? So this is the oxidized wafer you started with. So this has that oxidized layer, thin TOX, and then I need to open some pockets by etching. For that etching, we need to deposit a mask on it. So there is a mask using some polymers, some special polymers. Masks are created, like these are masks. This is a mask using some polymer, which is going to be resistant towards chemical etching. After that, the chemical will be put and it will basically etch only the exposed oxide. That means it will act only in the exposed region. The chemical etching will happen only in this exposed region. So after the etching happens, after the chemical reaction happens, it will basically eat up the oxide in this region and it will open that pocket. This mask needs to be created. So for every step that we discussed, we need to create masks. And this masks fabrication is the costly process. So in the entire MOSFET fabrication, you can see that I have still not shown all the steps. Every step will have multiple masks. And these are nanoscale masks, very small dimensions, nanoscale. They need to be positioned very accurately, nanometer precision, sub-nanometer precision. They need to be very accurately positioned. And then the processes like etching, doping, etc. need to be carried out. So once this is opened, you can apply the doping. The same mask can work on the doping also, because ultimately the opened area will only accept the doping. So after the etching, what will be the result? The result will be something like this. You are having again that you have etched out the oxide from the exposed region, and that mask is still lying on the top of it, polymer mask. And then now you can also do the doping here. You do the ND plus doping. That means you're applying N times doping. Now it will create the pockets, N plus pockets. Now the doping will not be able to penetrate the mask region. So below the mask, you also have the oxide. So other region will not be doped, only this region will be doped. And then after that, you can remove this mask. So you can have another process in which the mask can be removed, and then you get the this particular structure. This structure, and then you deposit SiO2. So why I'm elaborating on this? So every step will require this kind of mask, and basically the mask locations, dimensions, it all depends upon your circuit design. Where are you placing those MOSFETs? Where are you locating those MOSFETs in the entire chip? It depends upon that. So every chip will have its own dedicated mask. If you create a small MOSFET circuit, you want to fabricate it. Ultimately, in the fabrication process, you will have a bunch of transistors sitting in one single chip. And those transistors need to be fabricated at exact locations. Connections between them also need to be fabricated at different locations. So that will be done with the help of these masks. So for every fabrication process, these nanoscale, very accurate masks need to be fabricated. Their alignment needs to be made. The etching process, doping process, oxidation process, etc. needs to be carried out step by step to create all these MOSFET circuits in the silicon. Is this clear to all of you? Any question on
Yes,
this?
sir.
Now, if I talk about, say, the connection between MOSFETs, right? So we have also seen that ultimately the variation, the threshold voltage is going to depend upon all some of these fabrication parameters, like the oxidation that we talked about, right? The oxidation is determining the oxide thickness, and there also there are several parameters to be precisely controlled. So all those things will, decide the threshold voltage of the N MOSFET. Likewise, for the P MOSFET, there will be another process. So for the PMOS, what will you do? For the PMOS, you need what kind of substrate?
N-type.
N-type.
N-type substrate. So generally, again, there are different ways of fabricating P MOSFET. For older technologies, the bulk technologies, the standard processes say we can call this an N-well process. There are P well process also. It will become clear as we discussed. So in an N well process, what is done? So initially you have already doped the entire wafer. This entire wafer, we started with doping it with N type, sorry, P type. So for fabricating NMOS, you started with doping that entire wafer uniformly with P type impurities, P type atoms, so that you get you can fabricate your NMOS on the top of that P substrate. So we have created a P substrate. Whole wafer has been converted into a P substrate by doping them with acceptor impurities. And you have created your NMOSs. But for PMOS, we need a ND substrate, or basically N type substrate, donor type impurities. So what will be done in the N well process is we create a mask. Again, the same process. You will have to, on the top of the P type substrate, you deposit a mask. This is your mask layer. So I can draw it in some other color, maybe just for. So this mask I'm drawing in maybe sky blue color. This is your mask. And in the selected region, you are going to dope it. You are going to create an N well. So this is, you're doping it with donor type impurities, and you create an N well. Now, in this N well, this is your N well, because in the overall substrate was doped with the P type impurities, but now on the top of it, you have created small pockets called N wells, and there the concentration is mostly donor type. How do we, so effectively you might have seen that even if the initial silicon is doped with P-type impurities, maybe this concentration is something like, say, suppose this concentration is 10 to the power of 15 per centimeter cube. But if in this pocket, if you make the ND something like, say, 10 to the power of 16 per centimeter cube, then effectively, what is the type of dopant here in the green region? Because in this green region, yes, so somehow this discussion, my pen selection somehow creates problem. So if I click on this, I have to now it is not letting me select the colors. Either you have to remove this somewhere. Anyway, so I can select it from here, I guess. So draw. So in this green type region, because the overall dopant density is donor type, because in the substrate we had the acceptor type impurities with 10 to the power of 15 per centimeter cube, but in this pocket I have put ND, that means donor type impurities with a higher concentration. So resulting concentration will be ND minus Na. Net concentration in this is ND minus Na, because Na will give you that many holes. If you have acceptor type impurities, it will give you that many holes per centimeter cube. Now you put ND, it will give you that many electrons. So now, because this region has much more donor type impurities than acceptor, so this will have much more electrons than holes. Therefore, this region, the shaded region, becomes N type. Is that clear? Is that clear to everyone? How are we creating an N type well or an N well on the top of P substrate? So we have already made the entire substrate P substrate. On the top of it, we are creating an N well. And now I can just forget about the P substrate and I can repeat the process that we discussed for this N well. Now it is something like, if I just look at this N well, it is something like repeating the same process for PMOS, assuming that we have a N-type substrate in this region. Is that clear? So the same process will happen for PMOS fabrication, but it will happen in these N wells. Is that clear? Any question? Yes, any question on this? So once again, I need yes or no. It can't be a one-way traffic. You can't just keep mute in the class. Is this clear to
So it's
everyone?
yes, sir.
Yes, sir.
Now, so the next thing is, just a brief discussion about metal connection so that you know the physical structure, how the metal connections will happen. So already I have discussed, but, suppose you have two MOSFETs sitting side by side. Somehow this window has to be, either I have to hide this window or do something about this. So now the metal connections, you should have some more clarity how that metal connection will look like. So just like so far we discussed the MOSFET fabrication. Now, if you have say two MOSFETs, suppose we are talking about the connection like this, like the NAND gate, we need these connections. We have, these two gates, and output is somewhere here. It will be connected to PMOS also, but we need two NMOSes with this connection. This is the ground. This is the out. Now for that, there will be, first of all, there will be two MOSFETs, two NMOSFETs. So I can draw those two NMOSFETs. Likewise, there is another N MOSFET. So these two are there, and maybe I need the body contact also. So you have P plus body contact, P plus body contact. So this body is supposed to be connected to ground, and the source of this one is supposed to be connected to the drain of. So this is M1, this is M2. Let me call this M1. This is M2. So I need to connect the source of M1 to the drain of M2. These two regions need to be connected. Wait a minute. So now, how do we actually connect it? So as I told you, means after the MOSFET fabrication, we have multiple. This entire MOSFET will be covered with field oxide. This entire region will be, say, covered with field oxide. And on the top of that, there will be.
Sir, can't we use the same one N plus region for both the same purpose? Because like then we will not need any connection.
Sorry, same.
So can we use just one N plus region for the same two purposes? Means like if we just keep one single N plus here instead of two and keeping two and connecting them.
So I'm giving you one example where you need to have in general some metal connections. So this is just to explain. So in some circuits you may be able to share the N plus region. Like in this case, you can share the N plus region for source and drain, very much possible. But here this is just to explain the metallic connections. So now here this entire this top, the substrate is now covered with the field oxide. This is your field oxide. Now within that, above that field oxide is going to be another layer of metal, which we can call it as metal 1. So let me draw it in another color. So this is a metal 1 layer. This metal 1 layer can be now used to connect the gate regions as well as source regions, drain regions. Now, how do we go from here? So once again, using the mask and the etching process, remember how this metal 1 is going to look like? It is something like sitting on the top of that entire circuit, right? So just like you had the field oxide. So field oxide, let me draw it using whatever gray color. So this is your field oxide. This is your metal 1. Again, this gets deleted automatically. This is a problem with your OneNote. Somehow, sometimes it gets deleted. automatically. So this is your field oxide, and this is your, see, again getting deleted. So this is very annoying. So I will try one more time. I don't know what is this. Let me so see this one note has some discrepancies. Somehow I'm seeing that sometimes it is deleting whatever I'm drawing. So now coming back. So this is your, again, something is wrong. Is what is going on? Either or somebody is doing it. Have I given some remote control to somebody? Let me see. No, then how is it possible? It says that only I can edit, but somehow things are getting deleted. Anyway, so going back, let me try, maybe one more time. I have to. There is some control problem because the control panel of the MS Teams also comes and interferes, and then I have the control panel of the application. So both these things are interfering and creating problem. So somehow I have to get a better setup. This is very irritating. Some setting issue is there, which is creating conflict between these two control panels. Because this control panel belongs to MS Teams, and I can do without it. So there is no way to remove this. It there should be a way to turn off the annotation panel or control panel of the MS Teams, it seems, but let me see. I don't think this will have anything close. Yes. Anyway, so I have to look into this setup issue. Somehow a lot of problem comes because of this conflict. Anyway, so I can try to. So this is the field oxide, and then you have the top layer anyway. This is your metal one, and below that is your MOSFET structure. So field oxide, below the field oxide, you have the entire silicon structure. Right. So this entire MOSFET, etc., you're fabricating here. This N plus, and MOSFET. So this is coming here. So likewise, you will have other metal layers also, like you may have metal 2, which is going to again come another, after another layer of field oxide. So you will have a similar metal layer 3, metal layer 2, which is separated from metal layer 1 using another field oxide layer. This is another field oxide FO1, FO2, and this is M2. And this is your M1, lower one. Likewise, there are multiple metal layers, so separated by different field oxides. So at the bottommost level, you are having the silicon. You are fabricating the transistors on that silicon. In that entire surface of this lower region, you will have transistors fabricated, different slots, different spots, different locations. You have many transistors fabricated. But now, in order to form the connections, we make use of these metal layers separated by field oxides. So FO1 is separating the silicon with from the metal one. Likewise, FO2 is separating M1 from M2. Likewise, there will be M3, M4, M5, there are multiple metal layers. So in a given technology, the number of metal layers are fixed. So if you are using, say, TSMC 45, so TSMC is one of the foundries. So 45 nanometer, they may have a 9 metal layer process. That means in their technology, 45 nanometer, it will allow you to use up to 9 metal layers for making the interconnections. So here I'm just trying to show that how will the interconnection be formed. Suppose you are relying on the metal 1 layer to form the connection between source and drain of the M1 and M2. So for that, I will need to again etch out certain region. So what will I do? I will again apply a mask and I will etch out some regions of the metal selectively. So suppose I want only this region. So I will etch out the regions outside this. So I will etch out this entire region. I will etch out this entire region, and I will keep only these two. So for that, I can go to the eraser and I can just, I guess this one does not have eraser or what? I don't think this is an eraser. This is a problem. So this one does not seem to have an eraser. This is the eraser. Yeah, this is also just this dual control is creating huge amount of problems. So I have to get out of this dual control. Because this one doesn't seem to be having well. So basically, I want to get rid of this control panel coming from the teams, and that I am not very sure how to do that. Because I want to use only the control panel of the application, but somehow it is creating overlap.
Sir, hello.
Yes.
So I wanted to ask one thing that these metal layers which are put that you said that there are many metal layers separated by the oxides. So sir, do these contribute to any extra capacitances like for the chip? Won't
I will
they
discuss that.
act as
So there will be some capacitances which will come because of the interconnect that I will discuss. That is not directly with the MOSFET, but that will be related to the capacitances of the interconnect. But the first thing is I need to figure out this setup because this is very annoying and it is not letting me somehow get back to my, I have to close it either or do something. Let me just stop sharing once. If I stop sharing, then I have full control. But the moment I share that, MS Teams control panel pops up and that creates huge problem. I will share again. Let me see on the screen. Okay. but now I don't want to use. So this one can go to sleep. I can go to full screen. The moment I go to full screen, this control panel pops up of MS Teams, which I don't want. And this is a very irritating experience. Earlier, this feature was not there, but now it seems like this control panel automatically is popping up. But anyway, so now many things got deleted because whatever I had annotated using the MS Teams panel got deleted. But anyway, so I will. I hope you got the point, right? So somehow I have to avoid using the MS Teams panel, otherwise things get problematic. So back to the. Are you able to see the screen, all of you? Once again.
Yes, sir.
Yes, sir.
So just to redraw. So somehow this is a new feature where whenever I'm opening this panel or opening this application, MS Teams panels also starts coming, and then we get into trouble. See, this is okay. So now what I discussed was that just like you're having this metal one and this entire field oxide thing. What is the problem? Either I have to switch the application or do something because when I'm using this, something else is happening. Just let me delete this also. This is creating a huge problem. I have to change the application, otherwise it is uncomfortable to teach. Some changes they have done in the application which has messed up some things. But anyway, so see, again, I'm not able to select. So once again, just trying to capture the 3D view. So at the bottommost level, you had the silicon substrate on which you are fabricating the MOSFETs. N plus, the channel, the gate, all those things are there. And then on the top of that, you are having the field oxide. So this field oxide is separating. Okay. Something is wrong with the setup. I don't know how it is disappearing. So this is strange. Something to figure out because the cursor is in my control. There is no other person annotating. And how is it happening? So this is your field oxide. I can call it FOX. This is your silicon. And then on the top of that, you have metal 1. So on the top of that, you have metal 1. You again have another field oxide. And then see, getting deleted. I've never faced this kind of thing. This small window that is opening up, it is creating problem. How is it opening up? I have to figure out what is this window. I'm not calling this window. This cursor which is blinking is creating problem. So I have to figure out, because otherwise it is very difficult to use anything.
Sir,
What? So
uh, that brush with letter A on it is for handwriting for text.
this brush is what?
Like if you write any letters, it changes to text.
So I was supposed to do this. Okay. All right. So that's what I got confused between the two tools. So let me just use the gray color that I was using. So here we have the field oxide, FOX1, FOX2, and on the top of that again. So somehow what is happening is sometimes once this MS Teams tools pops up, it does not let me use the drawing tool of this application. That's why it becomes problematic. So now this is your M2 layer. This is M2. So this is how it is going to layer by layer. It is going to happen. Now the question is, now in order to make the interconnect, we saw that we need to make the source and drain of these two transistors connected. So I will use again the etching process. I will use a mask. I will use etching process uh, to remove some of these portions. So I will etch out the remaining connections. So this part I will keep and I will etch out the remaining. This part I will etch out using the mask. Remember how the etching will happen. Again, you have to use the mask and define this region. This region you have to cover. Sorry, just the opposite. So this region you have to cover using a mask and then apply the chemical here, etch this and remove this. So once you remove this, what will how will it look like? You will get this entire thing. So the metal has been etched out from this region, and now I have the connections only here. Now there is a via. So actually the via will be formed first before the metal diffusion. I have shown the reverse process. The first will be your via creation. So in this case, in the SiO2, in this field oxide itself, you will create holes. So this is like punching holes in the SiO2. So for example, in the 3D, if I show, it will be something like this. So you punch holes in that field oxide, and then when you deposit this metal one, it will automatically get into these holes also. It will fill the holes also. Are you able to visualize this?
Yes.
This is called via. The via is going through the field oxide. So first you covered the MOSFET using field oxide, and now you remove the metal from some region, and now you have metal region. In this case, you are patterning it only to certain region, and then you have the vias etched in the field oxide, which the metal will automatically fill. So this way we can basically create the connections between different MOSFET terminals. Likewise, we may have to use say metal 2 for connecting the body terminal of these MOSFETs to ground. So what will I do? I will in the 3D, how will it look like? In the 3D, we will have metal 1 edged out from some of these regions. So suppose metal 1 has been edged out. So metal 1 has been edged out, only certain regions are retaining that connectivity. And now you have a P plus contact, right? Suppose you have a P plus contact over here. You want to connect it to VDD, and VDD is going to connect to metal 2. So again, I will use another via. I'm going to use another via from the metal 2 layer, passing through all the way to the lower layer. So this via will connect the P plus to the metal 2. So maybe using another metal 2 connection, I can, connect the body contacts to VDD. Again, this metal to metal, this region is separated through field oxide. These regions are separated through field oxide. There is the field oxide FOX 2 here. This is FOX 1 here. And in between, all these connections are being formed by patterning the metal layers. So this is called patterning. The interconnects between transistors, different circuit components are done by patterning these metal layers. So ultimately, all this patterning will also require different masks. So based on your circuit design, based on the layout that you have done, physical layout that you have done, you will have a certain pattern created for the metal 1 layer, certain pattern created for the metal 2 layer. By your design, you define these patterns. And then based on these patterns, the connectivities are done. So this is just to give you a feel that what will be the actual fabrication process. And actually, these connections are made in the physical drawing. So the step 1 that you do in your circuit is schematic drawing, where you do the schematic symbols, you make the circuits. After you have done the simulation using that schematic drawing, fully satisfied with that, next step is doing the layout. Layout means once the schematic designs are done, device dimensions are fixed, everything is finalized, you are satisfied with the circuit simulation results, then you go ahead and do the physical design. In the physical design, we actually make use of these layers. So they are called layout tools. In the layout tool, we make use of these layers, M1, M2, polysilicon, your oxide, all these different layers to actually create the transistors at different locations and also make the connections using metal 1, metal 2 with appropriate dimensions, appropriate interconnects, etc. So this part you should be aware of. So the main motivation behind giving you this overview of application process was first to give you an idea that how the VT, the threshold voltage, will be dependent upon some of the fabrication parameters like the oxide thickness, work function, doping density, and so on. And second, the physical structure, actual connection between the MOSFETs in a chip, how will it be formed using this multiple layers of metal connectivities with the underlying silicon transistors. So this idea you should have, and definitely, we can. I think I will give you some more slides in which the more realistic pictures will be given, which will be good for the visualization. But ultimately, you understand that okay, how the connectivities are being formed. If you look at the top of any metal layer, like metal 2 layer, if you are trying to visualize how the pattern will come, it is a pretty complex pattern based on the way you have defined the connectivities. You have etching, you will have some parts having the metal, some parts not having the metal. So it will be a pretty complex pattern, nanoscale dimensions, which will be defining the connectivity between different layers. So if I say that how will the mask for M2 layer look like? So at some points you may be having metal 2 like this, sometimes you're having metal 2 like this, some places metal 2 is like this, some places it is like this. So, depending upon how you have formed the connectivity, the particular layer will look like, right? Likewise, metal 1 layer from the top, metal 1 layer may look like something else, right? So metal layer it may be, you may have formed connections in different ways. So the actual, the shaded regions are actually having the metal 1. So depending upon how you have formed the connections in the metal 1 layer, you will have certain pattern coming out of metal 1. Likewise, every metal layer, you will have some patterns coming out depending upon the way you have connected. This is a top view of the metal 1, metal 2, etc. Is this understandable?
Sure.
So now back to the main point. So we saw that the threshold voltage is strongly dependent upon some of the fabrication parameters. And these fabrication parameters, we try to be, as precise as possible. But again, in the fabrication process, there may be small variations. There may be, variations in the oxide thickness that you are depositing, because each of these oxide thicknesses, the oxide of the PMOS, NMOS are grown using different masks. And the process temperature, the time of exposure, etc., can have some variation, especially the temperature part can have some variation. So as a result, the doping concentration can also have some variation. As a result, it may be possible that you have designed a PMOS transistor or an NMOS transistor for a certain value of VT, but the entire fabrication process was such that the VT got shifted towards a higher value. So for an NMOS, you had targeted nominal VT, nominal threshold voltage VTN, approximately say 0.35 volt. But in the fabrication process, the oxide thickness happened to be slightly more, doping density happened to be slightly more. As a result, the actual VT, actual VTN came out to be 0.4 volt, got shifted. So likewise, the NMOS also it can have similar thing depending upon the fabrication process. So all the NMOSs now on an average, they will have a slightly different threshold voltage. So this is called process variation. So the fabrication process itself has been altered. Some parameters have been altered. It is not exactly as what we wish because of inevitable errors in the process. Some of the key parameters like oxide thickness or doping concentration or work function, etc., got slightly different as compared to the expected ideal value, and that directly has an impact on the threshold voltage. So now, based on this, either you get a higher VTN for the N MOSFET or lower. Likewise, for the PMOS, either you get a higher VT or lower, right? So as a result, we define process corners for transistors. How many process corners possible? So either this is your NMOS, this is your PMOS. So NMOS side, either it can be slow or it can be fast. PMOS side, it can be slow, it can be fast. What does slow mean? NMOS slow means what? VT is higher, VTN is higher. Fast means VTN is lower than expected. Likewise, VTP, mod VTP is slow means higher than expected. Fast means mod VTP is lower than expected. These are the four combinations. So slow corner means both PMOS and MOS is slow than expected. That means both PMOS and MOS VT value is higher than expected. Fast, this is FF, fast corner. That means both PMOS and MOS have VT lower than expected. Both devices are faster than expected. This is fast slow, this is slow fast. Right? So depending upon the way we are fabricating, after fabrication, your MOSFETs may end up in one of these corners. The entire chip may end up in one of these corners. So this is called a process corner. So you might have designed your VT, or the process might be targeting a VT of 0.35 volt, but the VT of the NMOS turned out to be 0.4 volt, or in some other fabrication, it turned out to be 0.3 volt. So that is the process corner definition. Now, if you have this kind of process corner variation, we can understand that just like we had seen the transfer characteristics of the inverter, right? So the transfer characteristics of the inverter depends upon the MOSFET sizing, effective drive strength of the MOSFET. So you may have designed the inverter to be having a certain transfer characteristics. This is the nominal, you have designed it to stay at a trip point of VDD by 2. This is, very nicely designed VDD by 2, VDD by 2 ratio is proper. But now, another thing that I also did not mention is the mobility. Mobility itself is another parameter which will vary a lot process to process. So now, if this is a nominal typical design that you have done, and apart from all these, there is a typical corner, TT. We call it typical corner, typical. This is the nominal corner, typical or nominal, which is having a nominal threshold voltages. So in the advanced tools, when you simulate, like the commercial tools which are used for actual designs, like Cadence, where you simulate the MOSFET circuits, you will have to select which model or which corner you are, willing to simulate for. So there is a typical corner and there are these four corners based on MOSFET. Typical corner means nominal values of the threshold voltage, both for NMOS and PMOS, TT, typical NMOS, typical PMOS. But then post fabrication, you can end up anywhere. And as a result, you need to make sure that whatever design you are doing, it is meeting the performance in all corners, right? Because it is not well controlled. You can end up in any corner. Therefore, any circuit design that we do, we simulate for all corners and try to make sure that it is working. That is the first thing you should be aware of. In this LT Spice, you may not get that kind of model. Right now in this model, you don't have this corner setup. But if you want to emulate, you can always emulate. I will tell you, like, just like, if you want to lower the threshold voltage of VT, in that model, you can go and edit the VT value or 5 ms value, doping value.
So we have in the model you sent, the 45 nanometer model which you sent, there it is there in the text file. Just slow, fast, and typical.
Okay, that is there. Then it is good. So in that case, you can do it directly. Otherwise, you can, in the older models, you can directly modify the VT value. So now, in this case, if this is a typical curve, what will happen if you have a fast corner? Typical to fast, what will be the situation?
So the curve will go
both
to the
are
right.
both are becoming, I would say, lower VT. So it is difficult to judge. It will remain almost maybe similar, or because the relative strength is remaining same for both of them. What if I say what is going to happen for slow fast corner? Slow fast corner means I'm treating the NMOS as fast, PMOS as slow. That means the NMOS VT is lower, PMOS VT is higher. What will happen to the curve?
Shift left.
So shift left.
Shift left.
Yes, shift left we have already seen, right? So this is going to be your slow fast corner. What will happen to the fast corner? Fast slow corner, just the opposite. So if you have the fast slow corner, it will shift towards the right. So again, although we may have designed a circuit for a particular corner, but the characteristics will keep shifting drastically from one point to another based on the corner that it ends up with. So this point we need to be very much aware of while designing any practical circuit. And this is related to the process corner. The process corner, here the assumption is that VT of all the MOSFETs on that particular die is getting affected in a similar manner. All the VTs of NMOSs, because the way it is fabricated, all the NMOSs will be fabricated using the same masks, right? So whatever masks are being used, whatever oxidation process is being used, whatever doping processes is being used, for NMOS fabrication, all of them, all the MOSFETs will be fabricated in the same step, right? Likewise, the PMOS, when you're doing the PMOS fabrication, N-well creation, gate oxidation of that N-well to get the oxide, and then the doping of source drain region, all those things will be done using the same steps. So all the PMOSs sitting in different N-wells will be fabricated in the same steps, right? Therefore, when we say that we are going for a particular corner, all the NMOSs will be getting affected in a similar way. All the PMOSs will be getting affected in a similar way. That's why we assume that the mean VT, the threshold voltage of all the NMOS shift in a particular direction, and VT of all the PMOS shift in a particular direction. That should be very, very clear. Any question on this? On the top of this is your process variation. There is something called random variation. So let us talk about briefly about the random mismatch or random variation. That is another important thing that you should be aware of. Random variations. Now, there are several sources of random variations. Like we are, one is, one example, one is random doping fluctuation, random doping fluctuation. As the name suggests, you are expecting certain doping concentration in the MOSFET, and that determines the threshold voltage. But now The different MOSFET which are sitting in different regions of the MOSFET can have slightly different Na, plus minus delta. It will not be exactly same for all the MOSFETs. It may have some random variation. Likewise, the oxide thickness also may have slightly, effective oxide thickness may, right now, if you look at it in microscope, it is very, scale technology is just few nanometer of the dimension of few nanometer. So if you look at the microscope, it will be something like, this kind of structure. Below that, you have the silicon. Effective thickness, effective TOX may also vary from MOSFET to MOSFET. Especially for smaller MOSFET, the variation will be more. Because if you have a bigger MOSFET, then this average, over a large MOSFET, even if it is having variation, over a large MOSFET, larger channel length, this will average out. But if you have a smaller channel length, the percentage variation in the MOSFET, oxide thickness, doping concentration will be more. That you understand statistically, if you have a bigger MOSFET, bigger channel length, bigger W, the randomness will be lesser and lesser. But smaller, the randomness will be more, right? Because if you look at the integration, if it's oxide thickness, for example, if I look at the effective oxide thickness, I will integrate the L effective oxide thickness in each of these delta L values and then make an average of it. So if you average over a large length, it will cancel out this plus minus delta L, right? Plus minus TOX. So in this direction, whatever plus minus TOX you are having, if you integrate it over a large L, plus minus delta TOX, I can write plus minus delta TOX. So if you integrate it over a large length, it will kind of cancel out. But smaller lengths, if you do, that cancellation will be lesser and you will get more random variation. So smaller MOSFETs will have more variation because of this imprecise or random variations in the doping concentration, oxide thickness, etc. Likewise, the work function will also have some random variation. Another thing is, say, line edge roughness, LER, line edge roughness. There also, ultimately, as the name suggests, when we are trying to fabricate the MOSFET gate, for example, we are assuming that it's perfectly top view, perfectly rectangular structure. This is a source, this is a drain, this is the contact. This is source drain, this is the gate, perfectly rectangular structure. But in the real scenario, no structure will be perfect like this. The gate will be, something like this. Oh, again, got deleted. So the gate will be something, like this. It will not be a perfect rectangle. It will have roughness, line edge roughness. And then you have to get the effective L. You integrate the L in the small segments and average it out, then you'll get the effective L. Again, if the overall L is big, W is big, you will get these delta L, small delta L that you're getting, it will cancel out plus minus. Whereas, if it is a small device, minimum size device, you will get more variations in the L. So this variations, if you have, say, variation in the oxide thickness, effective variations in the doping concentration, and even the channel length affects the threshold voltage slightly. So in case E people may not have studied it, but if your channel length is reduced, effective oxide thickness also gets reduced. That can be explained with the help of energy band diagram or with the help of potential also. So effectively what is happening is that if you're having your channel length very small, and then you are putting the source potential at 0, gate potential at some high value, whatever VDD or something, you are high value, and drain potential, you are keeping some VD. Now, or suppose your initial gate potential is, say, 0, starting with 0. Gate potential is 0, and the drain potential is some VD. Now, if your channel is very small, whatever potential you apply at the drain, it will have some effect in the channel, right? It will also affect the potential in the channel. So it will try to also create depletion region. It will also try to repel the holes and create the channel. If your channel is lower and lower, despite having the zero gate voltage, a positive drain potential may start turning on the channel partially, because it is going to create an electric field. It will push the holes away from the channel. It will start having influence on the channel potential. So effectively, you can assume that if your channel length is reduced, the threshold voltage will reduce. Therefore, if the delta L, so the L is slightly lesser, effectively, it will lead to lower threshold voltage. So all these variations, the effective delta L variation, oxide thickness variation, doping concentration variation, all these random variations, lineage roughness, all these lead to some random fluctuation in the threshold voltage. So what is the result of that? The result of that is that your MOSFET, you may be, if you are, having, say, the typical corner, TTD corner. So there you have assumed that threshold voltage is 0.35 volt for NMOS. But now, because of the random variation on that particular chip that you took out from that big wafer, right? You cut down, this wafer into small chip. When you are on this chip, there are suppose 100 MOSFETs, maybe hundreds and thousands and maybe millions of MOSFETs, but assume that right now 100 MOSFET. You measure the VT of each of these MOSFETs. Suppose you have some circuit through which you can, measure the VT of each of these MOSFET and plot the histogram over here. That means the number of MOSFETs having VT exactly equal to 0.35 volt. I will put some number over here, maybe, whatever number N1. Suppose 30 of them are having 0.35 volt. 30 out of 100 MOSFETs had VT very close to 0.35 volt. But then maybe some more, maybe 25 are having slightly higher, 0.375 volt. Likewise, some of them are having slightly lower, 0.325 volt, something, or 0.525 volt, yes. So maybe some of them, 25 are having something like this. And maybe a small number of them are also having voltages here, So you are having, say, 10 MOSFETs are having voltages 0.4 and some MOSFETs are having voltage of 0.3. So this is leading to a distribution. This is a histogram. In total, you have estimated a threshold voltage of 100 MOSFETs, right? So 10, 10, 50, 25, 25, 50, 10, 10, 20, and this is 30. So now this is going to give you a histogram kind of distribution, Gaussian distribution. So although my ideal value of the threshold voltage was this, but because of this random variation, my threshold voltages are having a distribution. If I pick up more and more number of MOSFETs, rather than 100, if I measure thousands of MOSFETs, they will also fit in within this distribution. Is that clear? So this is called, Gaussian curve. This is a Gaussian distribution. You are plotting the histogram of the VT threshold voltages measured from the MOSFETs in the chip. Now, if you had suppose this is a NVT, threshold voltage of the N MOSFET. Now, if you had a slow corner, whether the MOSFET threshold voltage was more, what will happen? What will happen to this entire histogram? This is a typical TT. Suppose now I have to plot the same thing for the chip in the fast or slow corner. Slow corner, what will happen?
You will shift right the entire
curve, the mean value will shift right, because mean value may be something like 0.4 volt, and the whole thing will, again, I'm not drawing to the scale. 0.4 will be just here, but just to exaggerate, I can just draw it to the scale also. So now the mean will shift here, right? If it was for a fast corner, maybe now the mean value will become lower. So this is for the fast corner. So now there is a mean value which is determined by the corner, right? The mean value corner dependent, but then on the top of that mean value, you are having spread in the VT values. That is determined by the random mismatch. So both these effects you need to be aware of, that it is not that all the MOSFETs in the chip will have ideally the same VT determined by the process corner. Corner may be something that corner will only determine the mean of the distribution. But then the sigma of the distribution, the standard deviation, that is the width of the distribution, how bad the variation is, that will be determined by the random variation. Is this point clear to all of you? Any question on this? So these concepts are very important in any practical circuit design. You need to be aware of both these process corner as well as random variations. So especially in analog circuits, it is much more important because whatever amplifiers, circuits, filters, differential units we are building, it assumes perfectly matched devices. And then in the actual circuit, we have this kind of variation. So both the process as well as the random mismatch need to be taken into account while designing practical circuits. And these challenges become more pronounced at advanced nodes. So the lower the technology node, more is the variation. Is this clear to everyone? Any question on this? Any question on this? Okay, so I think I have given you enough material for today. So I will give you some assignment based on whatever has been discussed yesterday. Today, it is just more about the theory part of the MOSFET fabrication, threshold voltage, and process and corner, also the random variation. So these things you should be very, very comfortable with. Basic concepts, fundamental concepts, and very much required for any real circuit design. Any question before we conclude? I have tried to avoid any detailed derivations of threshold voltage, etc. Conceptually, I just explained certain things. That much is sufficient in most of the cases. Yeah, I will try to find out some of my recorded lectures where some more detailed description of the physics is given. If you want, you can go through those. So before we conclude, any other question?
Sir, I have a question regarding the last class. The last class, you taught CMOS to build amplifiers using CMOS inverter, right? So
Yes.
there we used a feedback mechanism, that is a high value resistor, to self bias the inverter. But my question is that if I bias the inverter using a current source, it is if I build a current mirror and then bias it using the current source without applying the resistor, then will it still act as the amplifier or will it have a lower gain?
So that part you can tell me. You can answer that part. So let me draw what you are saying. So, I can go back. Maybe I have that notes here only. So if I go back to my sixth section, right? So sixth section, this. So towards the end, we had discussed this. So what you are saying is, whether if I, so how do you need to draw like exactly what you are saying. So this is what you have, and then what do you want to do?
So then I want to put a current source at the end by using a current, some sort of current mirror.
Here.
Yeah. Yes, sir.
Then
Sir, then I can mirror the current using some current mirror, which I have using some reference current source. Right on the left, maybe I have an NMOS current mirror from which.
so what? Like, does this mitigate the need of R, and are you still going to get gain from this
Yes,
circuit?
yes, sir. That's what.
What is the gain? How will you get the gain?
Sir,
Yesterday I already gave you the answer.
sir, like as the lower thing acts as the current source, just simply as a current source, then we can perform similar analysis as we did last class, right?
No, so the question is, what is the small signal gain of this circuit?
Yes, yes, sir.
Yes, hello. How will you calculate the small signal gain of this circuit? Yes, tell me quickly. Yes, quickly. How will you
So
find the
since
small
the
signal?
lowermost acts as a current source, just as plain DC current source, then we can basically open it and then we can apply the analysis.
Open it. Then what you are left with? Open circuit, it will work. Open it means this node will be floating, right? So what will you do with that node? Hanging circuit. Yes, tell me. The question is, if you have to calculate the small signal gain of this, what will happen? You'll have to again apply superposition. You have two devices, both are getting the input signal. So first you will try to get the gain because of the upper device, put this at AC ground, and then you have this one. So, and the output node is here. So what is the gain because of this? This is also AC ground. V in is here. What is the gain because of this? Yes, tell me, what is the gain?
Sir, GMP by GMN, GM1 by GM2.
GM1 by GM2. How?
It's because looking from the
Basics are not clear. The small signal model, how will you draw how will you model the lower path like this 2 and 3? How will it be modeled?
yes, that's right. Sorry, I did a mistake in this 1 by GM1. So if I look in the for the impedance of the lower path, then looking from the drain side, I have the impedance. So
You do one thing, you derive, and we'll discuss in next class. Very simple. You will get the answer. Derive and figure out what will be the impedance, and superposition side, what will be the gain. And second thing is, even if you get some small signal gain from here, the answer is that if you have this circuit, here you have the impedance as GM2 RO2 times RO3. Looking downward, it is a stack cascode device. This derivation we have done earlier. If you don't remember, we will try to address it later. And the output impedance is output node is this one. So you will get the overall gain is GM1. Here the RO is coming in parallel. So this is RO1. So RO1 parallel this entire thing. This is approximately equal to RO1. So the gain of this circuit will be GM1 RO1. But if you look at the second, if you are looking at the superposition of the second transistor, this you will put at AC ground, apply the input at this V in. Second is also at AC ground, and output is here. Now this here, what is the gain from input to the output V out? This is a common source amplifier with a source degeneration, and this resistance is RO3. So GM, this is upward. If you look at it, if I ignore the RO, effective RO of the lower one, so RO1 upon 1 plus GM RO3. So it is not going to give you much gain, right? This is not exact expression because now again you have to take into account the RO2 also, RO1 also. So this is because of the source degeneration, this second path will not give you much gain. Effectively, the gain will be something like this only, GM1 RO1. Even if you get this gain, problem is that you don't have proper biasing. So this bias current is not helping you in anything because it is giving you the fixed bias current. But what is the DC potential here? You don't know, right? So fixing the DC bias current does not mean that this DC potential is fixed. DC potential can be anything. You have just fixed the bias current, IB. But what is you have some AC coupling. So what is the DC potential here and here? V in DC and V out DC. They are not well defined. How will you solve for V in DC? There is no way to solve. It is a floating node. Is that clear?
yes, sir.
So V in case you are having capacitive coupling, you can't even solve for V in. It's a floating node. It will be determined by some random value will come based on the gate leakage, source leakage, whatever, some value will come here. It is not solvable. Ultimately, in the actual circuit, it will acquire some value based on the leakage current. We have not considered leakage current so far, but there are gate leakage current because of which some gate leakage will come from PMOS, some gate leakage will come on NMOS, capacitor will have some leakage because based on the ratio of the leakage current, you will get some value, but that is undeterministic. First of all, you can't even control the DC voltage. And as a result, you can't control where you are biasing the inverter in this transfer characteristics. If the gate voltage itself is not clear, you may end up here, you may end up here, you may end up here anyway. So if you are capacitive coupling, you can't really use this. If it is not capacitive coupling, or directly coupled with the DC, another option is directly coupled with the DC. Then also maybe you are fixing the DC, but then because of the input output is not same, input output is still, output is independent of input. A small variation in the MOSFET parameters can shift the curve this way or this way, and as a result, you will end up again into unwanted regions. So again, this is not a practical solution. You're not getting any benefit from it. Is that clear?
Yes, sir.
Any other question? Any other question before we conclude? You will get some assignments. Please finish those assignments before tomorrow's session, and then we will continue. Okay. Last chance. Any other question?